In this video, we're going to do a more formal derivation of the equipartition theorem, which gives us a relationship between the energy and the temperature of systems, where energy is stored in quadratic degrees of freedom. What that means is that the energy is dependent on the square of some variable. So 1/2 mv squared, kinetic energy depends on the square of the velocity, 1/2 kx squared, the spring energy depends on the square of the displacement. So any energy that is stored as a square of some variable, we can use the equipartition theorem for. We're going to write this variable as q. This could be velocity or position or angular velocity, any of those things. Okay, so what we're going to do is we're going to write down the partition function for this energy, these energy states, which is going to be the sum over the states. So we are going to have some distinct values of q, and we're going to sum up the Boltzmann factor for each of those q values. Okay, and now what we're going to do is we're actually going to try to multiply this by some delta q divided by delta q. So by multiplying by delta q over q, we can write our partition function in this way here. And specifically, looking at this sum, well, I can graph this. So this is a graph of my Boltzmann factor, that is the Gaussian shape. And delta q is some width. So what I can do is I can take the sum of my Boltzmann factor by some width over all possible q values, right? So that is simply adding up the area of each of these chunks, because the area of the chunk is going to be the height, which is my Boltzmann factor, because this is a graph of the Boltzmann factors, multiplied by my width, delta q. Now, the sum of all of these areas, as long as my delta q is narrow, will actually be well approximated by an integral instead of a sum. And this is very nice because we know how to actually analytically evaluate integrals. So with this being said, we can change our delta q into a dq, and then we have this 1 over delta q hanging out front, which, well, we're a little worried about because I'm not exactly sure what this width truly is, but it's actually going to turn out that this 1 over delta q will cancel out in the end, and it won't matter what that is, as long as it's small enough that this integral is a good approximation for us. Okay, so now what we need to do is we need to actually evaluate this integral, and our limits are from -infinity to infinity. So in the energies that we are interested in, for example, kinetic energy, we can have infinite positive velocity or infinite negative velocity, right? There's no limit, if we're not talking relativistically, on our possible velocities for our particles inside of, say, an ideal gas that has some velocity for its particles, right? So we're going to integrate from -infinity to infinity over this integral here. The best way to do this is first to do a substitution. So we're going to let x equal the square root of our exponent. Dx is going to be equal to square root of bc dq. So we're going to switch from q's to x's, which leads us to this form here, where we have an extra square root of beta times c in the denominator from replacing dq with dx. And our integral is now over x. Luckily for us, this integral from -infinity to infinity of e to the minus x squared, which is a Gaussian function, actually has a closed form, and that is equal to the square root of pi. So now what we have is we've been able to actually evaluate this integral and get our partition function in terms of just constants and our beta, which includes our temperature. Remember that beta is 1 over k times t. So we have our temperature included in here, and then we have just 3 constants. Now that we have our partition function, it's time to find our average energy. So the average energy can be found using the equation 1 over the partition function multiplied by the partial derivative of the partition function with respect to beta, with a minus sign out front. Okay, well, The derivative of our partition function with respect to beta looks like 1 over delta Q square root of pi times C times negative 1 over 2 beta to the 3/2. If we then write 1 over our partition function explicitly out front, we see that the delta Q's cancel, the square roots of the beta and the pi's cancel, as does the C, and the only thing that is left over is 1 over 2 beta. And if we remember that beta is just K times T, this gives us 1/2 KT. So the average energy of a given particle that has 1 quadratic degree of freedom is 1/2 KT. If we want to find the total energy of a, say, ideal gas filled with particles, all of which have 1 quadratic degree of freedom, then U is going to be the total energy, is just going to be the number of particles multiplied by the average energy, which is going to be 1/2 NKT. This doesn't mean that every single particle has energy 1/2 KT. It just means that on average, their energy is 1/2 KT. So I can find the total energy by multiplying the number of particles by the average energy. Now, if I think about a system that has multiple degrees of freedom, for example, an ideal gas that could be moving in 3 independent directions, X, Y, and Z, then I would have a 1/2 NKT for each of those degrees of freedom. And I could find out my full partition theorem. The energy is equal to F over 2 NKT, where F is the number of degrees of freedom that I have.